So this week, we're very glad to have Zongchen Chen from Georgia Tech to tell us about optimal mixing of Glauber dynamics, entropy factorization via high-dimensional extension.
Thank you very much. And I'm very happy to be here to present our work about the fast mixing of the Glauber dynamics. And this is my joint work with Kuikui from University of Washington and my advisor, Eric Vigoda from Georgia Tech. And so my talk consists of two parts. The first part, I'll give some backgrounds and summary of our results. And the second part, I will discuss the outline of our proof approach and techniques. And so let me begin like the topic of my talk, which is about the Glauber dynamics to sample from a spin system. And so we will be, I will discuss like a very general setting where the space is basically a product, discrete product space. And I use Q to denote a finite set of labels or called colors or spins. And usually it's 0, 1 or plus minus or true false. And when it's not binary, like it can be denoted by Q colors, like denoted by 1 to 2 QQ. And also we have a finite set of variables or called vertices, and this is denoted by V. And every configuration will be an assignment of colors or spins to all the variables. And so this is a configuration, and we will look at some distribution over all configurations. And this is called the Gibbs distribution, where every configuration, the probability density of it will be proportional to some weight function, W. And in particular, this Z here is the normalizing constant for this distribution, and it's called the partition function. And I want to remark that, so since the number of variables is n, and the total number of configuration is large, so this partition function can be hard to compute exactly or approximately, and this distribution can be hard to sample. But we want to look at when there is fast algorithm to generate samples approximately from this distribution mu. So this is like a very general setting. So for this course, I'll mainly be focusing on a special class of spin system distributions called the spin system or graphical models. So these are like class of distributions where this weight function W well depends on the graph structure of some underlying graph G. So the distribution is defined upon a graph. And examples including like easy model, hardcore, or coloring, or matchings. And they are all originate from the statistical physics, but are now widely used in applied statistics and machine learning. And so let me give you a very concrete example, which is perhaps the most popular example of a graphical model. So this is the easy model. So for easy model, it is defined on graph G, and the label or the colors are usually denoted by plus or minus. But so for in this talk, for illustration, I'll use the red and the blue color to denote the two spins. And we will have a parameter beta, which represents the strength of the interactions. And the Gibbs distribution is given by that the probability of every two coloring is proportional to beta to the number of monochromatic edges. So for example, if your graph is cycle of interval and your configuration is all red configuration, and then you have 4 monochromatic edges, and the weight will be beta to the 4th. And if you have like this alternating pattern, then it's just like no monochromatic edges, so it's just 1 over z. And z is due to the normalizing constant called the partition function. And it's also easy to see from the definition that If your beta is greater than 1, then when you draw a sample from the Ising model, you are more likely to see a neighboring vertices to be the same, like aligned with each other. So this is called a ferromagnetic or attractive. And when beta is smaller than 1, you are more likely to see like two vertices, neighboring vertices to be opposite of each other. And this is called anti-ferromagnetic or repulsive. So this is the definition of Ising model, and like one example of problems that we studied, like how to generate samples from the Ising model. And we will consider the Glauber dynamics, or also called Gibbs sampling in the but usually in the continuous space. So this Glauber dynamics is a Markov chain to generate a sample from mu, and it does the following. So we will maintain a configuration, and in every step, we will pick a vertex uniformly at random, and for all the other vertices, they keep their same spin, the old spin they have. And for this picked vertex, we resample its color, condition on all the other vertices. So like here, this vertex, so since it has one red neighbor and one blue neighbor, the marginal probability condition on this condition on other vertices is just half-half. So we just pick a color for it. And the next step, we still pick a vertex. And this time, since it has three red neighboring vertices, the marginal probability becomes like beta cubic over the normalizing constant. And we update it. And it's not hard to show that if when we update, we use the right like conditional marginals, it will eventually converge to the Ising distribution. And the problem we study like how fast this dynamics converge. And this is captured by the notion of mixing time, which is the number of steps it takes to be within a small total variation distance, even when you start from a worst configuration. And so this is like the main problem we study. And for the Glauber dynamics, like on the Ising model, it turns out that it is closely related to some phase transition called the uniqueness, non-uniqueness phase transition. And so the next few slides, I'll introduce these phase transitions. And so statistical physicists, they use the Ising model to study phase transitions for materials. And a particular example they study is the ferromagnetic Ising model defined on the integral grid. And they found that there is actually a critical value for the parameter beta, which is 1 plus square root 2 in our setting. And they found that for the ferromagnetic case, when beta is smaller than this critical value, that's when the interaction is relatively small. And in this region, when you draw a sample from the Ising model, most of the time you will see half of the vertices to be red and the other half to be blue. And this is called disorder phase. And also, if you look at two vertex, then their colors, the correlations between the two random variable will decay with their graph distance. And also, if you look at the Gibbs measure on the infinite grid, there is a unique one. And so that's why it's called uniqueness and non-uniqueness phase transition. And also when beta is large, that's the region that you have strong interactions. So in that region, when you draw a sample from the Ising model, you will see almost surely that one of the color will dominate. And also you will have long range correlation, means that two vertices might have strong correlation even if they are very far away. And also you will have a multiple Gibbs measure on the infinite grid. And it turns out that this threshold, beta critical, is also the computational threshold for the Glauber dynamics. In particular, if beta is small, when you have a weak interaction, the Glauber dynamics will converge in order n-logn steps. And meanwhile, if beta is greater than the critical value, it will converge in exponential in square root n steps. So here n is the number of vertices, and the square is square root n by square root n. So this is what was known for the grid. And but in this talk, we will be focusing on the Ising model defined on all bounded degree graph. And it turned out that for bounded degree graph, what's important is the threshold defined on the infinite trees. And so here is the figure illustration what happens for the Ising model, Faro Ising, defined on infinite delta regular trees. So for the tree cases, there's also this critical value, which is different from the grid, and which is actually easier to like compute or to verify. And also you have very similar behavior. So when beta is smaller than this critical value, you have some decay of correlations from the root to all the leaves. And you have a unique measure for the infinite tree. And when beta is large, this correlation will always exist like non-zero, and you will have multiple measures. And like I mentioned, so the important thing is that this tree uniqueness and non-uniqueness threshold marks a certain computational phase transition for the Ising model on all bounded degree graph. So in particular, let's look at the ferromagnetic Ising model defined all.
So this is a
all
tree
graph.
of depth n.
Sorry.
So this is the delta regular tree with depth n. Or n is the size of the tree, the size or the height.
This n is the number of vertex and delta is the degree.
Okay.
Yeah, and it's not height, it's the total number of vertices. Yeah, so but here the slide is about like so the figure here is about arbitrary graph. So it's the Ising model defined on arbitrary graph on n vertices. And so what I want to say is that this tree uniqueness threshold marks the phase transition for bounded degree graphs on n vertices. And in particular, when beta is smaller than the critical value, that's when you have weak interactions. The Glauber dynamics converge in nlogn steps. This is a result by Mosel and Sly. And also when beta is greater than the critical value, the Glauber dynamics will converge in exponential time. So n is the number of vertices. And also I want to mention that for trees, there's some slowdown when beta is large, but since you have special structure for the trees, it's always a polynomial, but with a large exponent. But for like in general, for general graphs, the Glauber dynamics can be exponential in n. And also another thing is that for the ferromagnetic Ising model, using the monotonicity or the special properties for the ferromagnetism, you can have other polynomial time approximate sampling algorithm, not using the Glauber. And this is a classic result of Jerome and Sinclair. And also Randall and Wilson uses that to get a sampling algorithm. And there are also other types of algorithm to do the ferromagnetic Ising model, like the Swenson-Wang dynamics. And this is given by the Guo and Jaren. And so what I've been talking about is the ferromagnetic case. And there's also this anti-ferromagnetic case. That's when beta is smaller than 1. And you can also define this uniqueness, non-uniqueness threshold on the tree. And for the anti-ferro case, the sampling problem actually is harder. So when beta is smaller than the critical value, that's when beta is far away from 1. So you have like large interactions. And for this region, Glauber dynamics can take exponential time. And actually, this is a region that there does not exist any polynomial time sampling algorithm or counting algorithm. assuming that RP is not equal NP, and this has been shown in recent years. And however, when beta is greater than critical value, that's when it's closer than 1 and has weak interaction. Previously, it's not known that how fast the Glauber dynamic is. And what we show is that it's actually converging optimal nlogn steps. And just let me give you a more detailed picture. So in the theorem here, I combined both the ferromagnetic and anti-ferromagnetic, and the left-hand side and the right-hand side are like the two threshold, and the little delta here measures your distance of your parameter beta to the uniqueness threshold. And what we show is that when beta is in this uniqueness region, it's converging delta to 1 over little delta times nlogn steps for all graphs of maximum degree capital delta. And in particular, this bound is also still polynomial, even if your maximum degree is unbounded. And below is the figure illustrate the whole picture for the Ising model. So beta greater than 1 is the Ferro case, and even if you beyond the uniqueness threshold, you can do other methods to get a poly n sampler. And when beta is smaller than the critical in the anti-Ferro case, it is computational hard. And the Moselle slide did the ferromagnetic case in the uniqueness region, and their proof uses a monotonicity of the system, and so it depends on the ferromagnetism. And what we do is we show nlogn for the whole uniqueness region containing both the anti-ferro and the ferro case. And our proof actually does not use anything about the ferromagnetism or the monotonicity of the spin system. And also a remark is that some people might heard about this Bruchian uniqueness. And this is like a slightly smaller, a strictly smaller region than the uniqueness region. And also in this region, it's very relatively, so it's pretty simple to show that the Glauber dynamics converge in nlogn steps. And so that's what we have for the Ising model. And for this computational problem, like to generate samples approximately from the distribution or to approximately compute the partition function, which the two problems are equivalent to each other. So for this type of problems, there's actually other methods to solve these kind of problems. And in particular, for the anti-ferromagnetic Ising model, where the problem itself is harder than the ferromagnetic case. And for this type of problem, there have been like two other types of algorithms. So the first one is using the decay of correlations. And this is given by Weiss initially for the hardcore model. And this approach uses the relation between graph and the self-avoiding work trees, and utilizes the decay of correlations. And for this algorithm, the runtime is some large polynomial, and the exponent is 1 over little delta times a log delta, so it's pretty large. And there's also another type of method called the polynomial interpolation. This is given by Barvanok and also had been applied to the Ising model. And so this algorithm uses the zero freeness of the partition function and uses Taylor approximation of the log of the partition function to approximately compute the normalizer constant. And for this algorithm, the runtime is also a polynomial, but the exponent is pretty large. So the exponent itself can be exponential in the maximum degree delta. And meanwhile, for Glauber dynamics, it's much faster. And so it's converging nlogn steps. And so Moselle slide did the ferromagnetic case using the monotonicity. And our proof, which uses like ideas from Anari, Liu, obvious Gaussian, which I will discuss soon. And but their running time is also a large polynomial, but we managed to improve it to nlogn. And moreover, so our results holds for not only the Ising model, it actually holds for a lot of spin systems. And so what we can say is that the Glauber dynamics converging nlogn steps for all these spin systems defined on a bounded degree graph, including like the hardcore model, which is weighted distribution as the distribution on all independent sets weighted by its size. And we show rapid mixing and nlogn mixing for all lambda smaller than the critical lambda, which is also the tree uniqueness threshold. And also we can do the anti-ferromagnetic two-spin system in general, which contains both the hardcore model and the anti-ferro Ising model. And we show that we show nlogn mixing when the parameter is up to data unique. This is defined by Li, Lu, and Yin, which is so roughly speaking, it's the same as the tree uniqueness threshold, but instead of looking at the data regular tree, you look at all trees with maximum degree at most data. And also our results apply to the coloring when Q is greater than 1.76 and the graph is triangle free. And this matches the other two methods like the decay of correlations or the polynomial interpolation. And also for matchings, this is the monomer dimer model, which is a distribution over all matchings weighted by size. And for matching for any lambda, we can get nlogn, but the dependency of the constant before, so the constant before the nlogn depends on the maximum degree data and the parameter lambda. And I want to remark that it's actually known that it's a classic result of Gerron and Sinclair that the Glauber dynamics converge in n cubic log n time for any graph. So here the n just means we don't require the degree to be bounded. So the degree can be as large as order n. But our result, our running time actually is exponential in the maximum degree data. So this is like summary for results of other models. And next I want to say that we actually have a very general statement about the Glauber dynamics, which implies all these specific models. And in general, what we show is that we consider any Gibbs distribution defined on a graph of maximum degree data. And in general, we show that if this Gibbs distribution is marginally bounded and spatially independent, which I define very soon, then this Glauber dynamics for sampling from this distribution mu will converge in nlogn steps. And so just roughly speaking, this marginal bondedness just means that all the marginal probability at a single vertex is bounded away from 0. And the spatial independence condition is defined by Anari, Liu, obvious Gaussian, which actually start this line of work for analyzing the Glauber dynamics. And this condition just roughly speaking says that the correlations decays with the distance, but they state it with more like a spectral way. And I want to say that the paper of Anari, Liu, obvious Gaussian, they define the notion of spectral independence, and they show that the mixing time is n to the order eta, which is a large polynomial, but we managed to improve it to be nlogn. And also, so for this general statement, general theorem, when we want to apply it, usually this marginal bondedness is very easy to show. So you get it from the definition of the model. And this spectral independence, which is like the decay of correlations. And since it has been proposed, has been established for many specific spin systems. So the paper of Anari Liu, obvious current, they showed it for the hardcore model when the parameter is in the uniqueness region. And later on, we showed it for the antiferrous two spin systems. And also there are two groups of people both showed it for the coloring on triangle free graph when Q is greater than this threshold, which matches what had been known for the correlation decays or the zero freeness of the partition functions. And also for the monomer dimer, we also establish this spectral independence for any parameter lambda. And so since we can show spectral independence and the marginal bound, we can get nlogn for all these models. And so these are just the key results we have, which implies all the fast mixing result for all the models. And next, I'll try to explain in more detail the definitions of the marginal bondedness and the spectral independence. And before I define them, let me introduce just some remarks and assumptions. So first, I'll always assume that our distribution is soft constraint model, which just means that the distribution mu is fully supported. And so the definition I'll introduce later is always about soft constraint model, like the easing model. And for the hard constraint model, like the hardcore correlating, where not every configuration is allowed, these definitions need to be changed with some very small modifications. And the second thing is that I introduce the notion of pinning, which is basically you take a subset of vertices and a coloring or assignment of spins to these vertices. So this is just called a pinning. And we will consider the conditional distribution induced by this pinning, which is denoted by mu s of tau, which just means vertices outside S will be fixed to be the partial configuration tau. And we will look at the marginal distribution on vertices in S under this conditioning. And next, so first I'll introduce, I define the marginal bondedness, which basically says that the probability of every vertex receiving every color is at least B, some constant B. And in particular, this is defined under any pinning. So here, the S, lambda, and the tau is just an arbitrary pinning. And we want the probability of the color of V to be I is at least B for any V and I. So that just means that for any under an arbitrary pinning, the marginal probability of every vertex and color is at least B. And an example is the easing model, where it's very easy to show that the worst case, like the worst case marginal is the minimum over beta to the delta and 1 over the normalizing constant, which happens when all your neighbors is monochromatic. So like this is the probability of a vertex V being red or blue when all your neighbors is all blue. And just a remark that for hard constraint model, so since this marginal can be 0, the definition will be changed to like all non-zero probabilities is at least B. And the second notion is this spectral independence, which captures the decay of correlations, but in a spectral way. And also we will have an arbitrary pinning. And under any pinning, which induce some conditional Gibbs distribution. And for this conditional Gibbs distribution, I want to define a certain influence from a vertex to another. And in particular, for multi-spin systems, this influence is given by from one vertex color pair to another vertex color pair. And in particular, the influence from UI to another pair VJ is given by the difference of the probability V is equal J, conditioned on U equals I or not. So basically this difference is that how much does the marginal of V is colored by J changes when you know that when the condition is that U is colored by I. And so for every two different vertex spin pair, we can define this influence. This gives you a certain matrix, and the spatial independence just says that under any opinion, the maximum eigenvalue of this matrix is upper bounded by some constant eta. And I just want to remark that for any opinion, you have a conditional distribution, so you have a different influence matrix, and the condition is that the spatial independence that defines that for any opinion, all such influence matrix has bounded maximum eigenvalue. And so this notion is first defined by Anari, Liu, Ovius, Garvin. So they defined it for two spin system like Ising model, and later on the other two works define it for the multi-spin systems. And also I want to say that there's other notion which is called strong spatial mixing, which also captures like the decay of correlations. And actually like the current proof, all the current proofs for spectral independence is basically following the same proof as for the strong spatial mixing. And meanwhile, on the other hand, the reason is that for the maximum eigenvalue, when we trying to actually prove the spatial independence, we usually just first bound the maximum row sum or maximum column sum of this influence matrix, which is kind of the sum of influence from vertex to all the other vertices. And that's why we have this similarity between the decay of correlations and strong spatial mixing and this spectral independence notion. But also it's unknown like if this spectral independence is stronger than the strong spatial mixing, or it's weaker, or they're equivalent or not, is still unknown. And so given this, all the definitions of marginal bondedness and spatial independence, so our the key result is that for any Gibbs distribution of some spin system defined on a bounded degree graph, graph of maximum degree data, if it has a good marginal bond and the spectral independence condition, then the Glauber dynamics will converge in nlogn steps for sampling from this distribution. So it's a very general statement and holds for all these models I mentioned, like the Ising model or hardcore or colorings. And so that's the key result. And the rest of the talk, I'll be discussing the outline of our proof approach, which involves like entropy, tensorization, and factorization, and also the framework of simplicial complex to study the Glauber dynamics, and also this local to global argument for the entropy contraction in the framework of simplicial complexes. And so that's a good point so if you have any question so far, before I'm moving to the proofs.
So I wanted to ask you about the matrix. Was that? Yeah. So is it clear that its eigenvalues are real? It doesn't look like it has to be symmetric. Or is it symmetric?
This matrix is not symmetric, but the eigenvalue is always real, because so this influence matrix is actually, it comes from some transition matrix of some random walk on the space of vertex spin pairs. And so actually what happened is that we defined a random walk on the space of vertex spin pairs. And for this random walk, we have this transition matrix, and we just like minus CI and do some transformation, we get this influence matrix.
Are you going to discuss this later on?
Yes.
Okay.
Yeah, so maybe let's move on.
Actually,
so, yeah.
sorry, can you say anything about the constant in front in your theorem? Like how does it behave in terms of this delta beta, particularly?
Yes. So I just write it as so it scales something like this. So delta is maximum degree, and the B usually is, so I'll say usually it's 1 over delta, at least for all the applications we have. And the eta is usually like or the 1 over delta, where this little delta is like the distance from your parameter to the uniqueness threshold, like the theorem in the Ising model.
Okay, thanks. That's
Yeah,
pretty
so
precise.
yeah. Yeah, so let's move to the like ideas of the proof. And so like
Sorry, can
on
you
a
go
very
back
high
to the
level.
statement of the theorem for a minute?
Yes.
It was just a bit fast. So
Yeah, since we are looking at this theorem, so one like open problem is like to get a better dependency on all these parameters for the constancy, and especially for like our result here depends exponentially in the maximum degree data in some applications, but I mean hopefully we should get a polynomial dependency on the maximum degree or even logarithm dependency. Yeah, so currently it works well for sparse graph, but not the dense graph. So maybe move on.
So I'm a bit bothered since it's not clear where the structure of the graph comes into the theorem. So do you assume that the Gibbs measure is based on nearest neighbor edge interactions?
Yes. That's a good question. So here the spin system. So I didn't like give a formal definition, but I only look at nearest neighbor interactions. So
just along the edges, so just in pairs.
yes, just along the edges,
Okay.
like that's the form of the interactions. So along edges, that's right. And for the proof, like the very high level, what we did is we tried to establish the modified log Sobolev constant for the Glauber dynamics. And let me first just introduce some standard notion, functional analysis notion for like Markov chains. So mu would be some distribution, and f would be some function, and the expectation of f, which is denoted by E mu f, is basically you took a configuration and the f of that in expectation. And the entropy of f, which is the expectation of f log f over the E mu f. And these are standard notions. And in particular, for if you are not familiar with the entropy, you can think of it as describing the fluctuation of a function f with respect to the distribution mu. And in particular, if the entropy is 0, then your constant is your function f is a constant function. And also if your function f is the relative density of another distribution nu over mu, then the entropy just describes the KL divergence. And what I want to define next is I call it the local entropy. which is defined. So I want to say how much the fluctuation is of f at a single vertex. And so to define this, I take a vertex v, and I take a pinning of all the other vertices, and I have this conditional distribution at v, given all the others being colored by tau. And then for a function f, I can define the entropy with respect to this conditional measure, which is denoted by entropy at v given tau of f. And so I want to say that the function f takes the whole configuration as input, but since everything except v is fixed to be tau, so here it's kind of just a function of the spin at v. And also this entropy depends on the pinning tau. So you can view this entropy as a function of tau. And in this sense, you can take expectation, which is you take a tau and compute the entropy at v given tau. And so this kind of describes the average local fluctuation of the function f at v, at least as one way, like how I think about it. And what's important about this notion is the so-called approximate tensorization of entropy. And so this is a functional inequality, which says that for any function f, the entropy of f is upper bounded by constant times the sum of all the local entropy at each vertex. And one way of thinking about it is that the fluctuation of f is attributed to the sum of all the local fluctuation at every vertex. And or another way to say it is that if you know this entropy, this local entropy is at most like epsilon over n, and the total entropy will just be order epsilon. And so this is like a notion that has been studied for many years. And in particular, a very well-known result is that for product distribution, you have this approximate tensorization holds with an optimal constant 1. And that's in that case, it's just usually just called tensorization. So it's basically the tensorization for the product measure. And so in this sense, this approximate tensorization describes how far away your distribution is from a product distribution. And what's important about this notion is that it implies an optimal mixing, asymptotically optimal mixing time of the Glauber dynamics. And it's not hard to just write it that if you have the approximate tensorization, and then after each step, here P Glauber is the transition matrix. So after each step, your KL divergence to the stationary distribution will contract with a rate 1 over C1n. And also, if you have the tensorization, then the spectral gap and the modified log Sobolev constant is at most like 1 over C1n, which is asymptotically optimal. And so I won't define these two notions in details, but they are all like standard notions in the study of Markov chains. And I want to discuss next is like a slightly generalization, but important generalization for the tensorization, which we call it the uniform block factorization. So the left-hand side is still the entropy, and the right-hand side, so instead of you consider sum over all the vertices, here we look at sum of overall subset S of a fixed size L, and we look at the sum of the entropy at local entropy at S. And here the 1 over n true cell is basically n true cell is basically the number of such subsets, and the L over n is just some normalizing constant. And in particular, if L is equals to 1, this is basically the same as the approximate tensorization. But for our application, we will mainly consider this L to be linear in n. And the reason is that This is inspired by the recent work on general block factorization by Caputo Parisi. They study like arbitrary block and arbitrary weight. And also it comes from the simplicial complexes, which I'll discuss soon. And from there, they kind of also looking at, they are looking at a uniform subset of a size L. And also we have this fact that this uniform block factorization holds with an optimal constant 1 for all the product distribution. So this is just some generalization for the tensorization. And the key thing is we have here is that we will consider linear size blocks. And what we can show that if you have a linear size block factorization with a very small constant theta, then you have this, you can get the approximate tensorization. And this in some sense gives a comparison for the single side block dynamics and the uniform block dynamics, which is the dynamics that in every step you pick L vertices uniformly at random and update them. And this comparison holds for the variance as well, which is basically the same as comparing the spectral gaps. But so it does not provide a direct comparison for the modified log super constant, but it's good enough for our application. So basically in order to show the tensorization, we only need to show this uniform block factorization with a linear size block. And just to give you some intuition for this theorem, what we can show is basically the proof of theorem is actually not hard. So it basically says that if you took a random S of size theta n, uniformly at random and theta very small, then this subset S, which is the green part, will shatter. And this just means that since it's n over 1,000 delta, this induced subgraph G of S will contain many connected components, and each of them will have a constant size in expectation. So the local entropy at S will tensorize because different component, the distribution will be independent of each other. So it will tensorize to each component, and every component has constant size in expectation. So it further tensorized to single vertices, and that's how you get from the block factorization to the tensorization. And so this actually gives the first part of the proof, where you use you get from the block factorization to tensorization and then to mixing. And what we will discuss next is how to use the spatial independence to get the block factorization of the entropy. And so actually the blue arrow here does not use the spatial independence notion. It just uses the structure of the graph because the graph is sparse, has maximum degree data. And meanwhile, the other part will use the spatial independence notion and actually does not require max bounded degree. And so let's move to the second part, which we want to show the uniform block factorization. And so let me first discuss what's being done by the Anari Liu OVS Garland paper. So for that paper, what they did is they look at the Glauber dynamics from a different point of view.
Sorry, which paper is that?
Yeah. Sorry.
Which paper is that?
This is, so I'll show you soon. It's the Anari Liu OVS Garland paper. So it will show up. So yeah, let me just introduce first the Glauber dynamics. And so the framework is that as they look at this Glauber dynamics as dynamics from all the full configurations to all the partial configurations on one less vertex. So for example, if you start from a configuration and then you, what you do is you remove a vertex, resample the color of one vertex. So this is equivalent to removing one vertex, and you get a partial configuration, and then you move back, and this time you recolor this vertex with the correct marginal probability. And so this is the paper, the Anari Liu OVS Gavin. And so they basically view the Glauber dynamics as a random walk from the set of full configurations to partial configuration with one less vertex. And this is actually, like in general, this is fits in the framework of a general simplicial complex. And in particular, this is called the down-up walk in the language of simplicial complex. And so for simplicial complex, you can not only do like a full configuration to partial configuration, you can actually do between any two levels with dimension differ by one. So particular for like spin system or product distribution of product space, this would correspond to a random walk between like a partial configuration on k vertex to a partial configuration on k-1 vertex. So for example, in this example, we can also define a random walk from a configuration on two vertices to a configuration on one vertex. And in each step, we will first just remove a vertex, and which we pick uniformly at random, and it move from a two vertex to one vertex. And then we will move back, which would correspond not only we need to pick a vertex, which is not in here. So we need to pick a vertex and pick a color of it. And so this kind of, you can define a certain random walk between configuration on two vertices and configuration on one vertices. And further, you can define this random walk from level 1 to level 0, which is the trivial one random walk. So what they did is you can look at this Glauber dynamics in the framework of a general simplicial complex. And so I won't define the most general version of simplicial complex, but what I will say is that you can think of it as some collection of subsets. And in particular, for at level n, you will have some collection of all size n subsets of some ground set, and the pi n will be just some distribution of it. And you will have then for every k smaller than n, you will have xk to be the collection of all size k subsets of these sets at the top level. And the distribution would just be you sample configuration from top level and pick a uniformly random size k subset of it. So that's kind of give the definition of a pure n-dimensional weighted simplicial complex. And one like most typical example is probably the matroid. So xn would just be the collection of all the bases of this matroid, and the pi n can be any distribution, weighted distribution over all the bases. And for smaller than k, smaller k, like xk would just be collection of all the independent set of size k's, and pi k would be the induced distributions. And so here I'll be mainly talking about the spin system. So the ground set will just be all the spin vertex pairs. And so at the top level, you have the full configuration. And at level k, you have partial configuration on k vertices. So in particular, it's a pair U and tau. U is a subset of size k, and tau is a configuration on U. And the probability, the distribution at this level k is 1 over n choose k, which is the probability you selecting this subset when you consider this subset is selected uniformly at random. So it's 1 over n choose k times the marginal probability that U is colored by tau. So this will gives you not only the top level, which is the same as the Gibbs distribution, it gives you the whole, like a distribution for all the partial configurations as well. And the important thing we'll be looking at is the contraction of the entropy in this framework. And this is called which we call the entropy contraction. So at the top level, let's take some function which is defined on the top level, fn, and we can also get the function fk, which is defined as follows. So here the p up arrow represents the transition from level k to level k plus 1, but the definition is not important. You can just it's actually just the projection of the function fn defined on the top level to a lower level at level k. And so you have this projection, you get this function fk, f of k. And we will say this simplicial complex or this system satisfy this global entropy contraction. When you look at the lower level, the entropy at the lower level will contract compared to the entropy at the top level. And so actually by the data processing inequality, this contraction always exists. So the entropy is always no bigger than the top level, but we want like a non-zero contraction. And if we have a non-zero contraction, this is called the entropy contraction for which holds for NAF. And this notion is studied for the matroid, which, like I said, is a special case of the simplicial complex, or more generally, the strongly log concave distribution. And this is studied by the Kuikui Mosa. And so for our result, like a key thing, and actually the reason we study this uniform block factorization is that for this simplicial complex or this framework, looking at all the full configuration and partial configuration, the order 1 minus theta n global entropy factorization is actually equivalent to the uniform block factorization of the entropy for the original distribution. So it's actually two equivalent notion. And in that sense, to show this global entropy factorization, we only need to show this uniform block factorization for mu, we only need to show the global entropy contraction in this framework of the simplicial complex thing. And that's why where we can use this local to global argument. So this is like this is an approach that has been studied in recent years. Like people want to study the down-up work and up-down work in an abstract weighted simplicial complex, and they define this local to global argument. And a key thing is that for this simplicial complex in our setting, which are the order configuration and partial configurations, you can look at the pinning, which say the red vertex, the circle vertex is colored by red, and you can look at all the partial configurations and configurations that containing that the circle vertex is being colored red, and this will define like a simplicial subcomplex, like a subgraph. And in particular, the spectral property of the global works can be described by the spectral properties of the local works defined on this simplicial subcomplex. And this is basically the idea of local to global approach. And so for like, here is the detailed definition, but I probably don't have time for that. And the idea is just you look at all the configuration contains certain pinning, and the local work is defined upon this this link, this simplicial subcomplex, and it's between the level 1 to the top level and then back, and the non-lazy version. And actually this spectral property of this local work is described by the influence matrix. And this kind of answers the previous question of Jonathan. So basically, this influence matrix comes from the transition matrix of this local work, which is defined upon for any pinning in the simplicial subcomplex or links. And if you have the spectral property of all the local work, you have the spectral property of the global work. And what we do here is that we use this local to global framework argument, but we did it for the entropy. And in particular, we show if you have the certain notion of local entropy contraction, which is the entropy contraction in the link in the simplicial subcomplex. And if we have the local contraction, we can get the global contraction. And also we can further reduce the entropy contraction to the spectral expansion, which is the spatial independence. And also such a result can be also done for the variance, which is kind of, which is what's being done by the result of Aleph Lau and Anari Liu obvious current. And that's kind of the idea of the whole proof. We get from spatial independence to local entropy contraction and then to global. And from that, we get the tensorization. And just to a quick conclusion, we show nlogn for Glauber for a lot of spin systems in the uniqueness region or match the best bound. And the general result is that if we have marginal bondedness and spectral independence, and the graph is bounded degree, then we have nlogn for Glauber. And the open problem, like I said before, is to get dependency on the parameters. And that's all for the talk. Thank you very much. I hope I don't go beyond a little bit. And that's
thank
all.
you. Thank you very much. So everyone can unmute themselves. Questions?
I had a question. When
Yes.
you were talking about the approximate block tensorization, I think, maybe you can go back to that slide. I was wondering if there is any relation there between that and Shearer's inequality. So
Just let me first find it.
Yeah, this one, 28, I think.
Oh, this one, right?
Yeah, here.
Yeah, so if you mean Shearer's inequality is like, do you mean like this L to be like n-1? Or like the sub-additivity of the entropy?
Yeah, like sub-additivity, yeah.
Yes. Yes, that's a good point. So yes, so our results actually can show the sub-additivity of the entropy for the same range of the parameters.
Okay.
I will stop the recording here.